All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. Today, I want us to keep talking about condition variables. So yesterday, what we did was like hyper contrived. I want to build up this little program that has some threads in it. The threads are waiting on a condition variable. The main thread of execution signals them. They don't actually do anything, but they block and they wait until the signal arrives. The main thread signals them, they finish. The goal here was to kind of get us familiar with the semantics of condition variables. Acquire the lock, wait on the condition variable, and then release the lock and go to sleep so that other threads of execution can actually do things with the lock that we're working with here. Today, I want to spend a little bit more time taking a look at a more realistic example of how we would use condition variables. So I want to use condition variables to protect a critical section that's working with a data structure, a complex data structure, as opposed to just having contrived, like, get these tasks to wait around for something to happen. So the state that we were in yesterday was we've got locks. Locks have solved the problem of mutual exclusion for us. They're allowing us to have critical sections that are guaranteed to only have one thread of execution running in them at a time. But the big problem with them ultimately is that as soon as the lock is available, somebody's going to go into that critical section. And there are circumstances where we don't necessarily want that to happen. Condition variables allow us to do something like this. I can get a lock, and then I can suspend myself until an event happens, and then be guaranteed that I have the lock when I'm awoken. So when I'm told this event has taken place, I have the lock and I can do stuff with this data structure that I want to work on. So again, yesterday we did this hyper-contrived example that uses condition variables. And today what we're going to do is spend some time working with some realistic code that uses condition variables. The realistic example is going to take us on a little bit of a different path here. And so I know that you already had this class this morning, but hello, everybody. Welcome to Comp 3350 Software Engineering. Today, what we're going to talk about is I want you to be able to identify and apply design patterns that solve common software design problems. The realistic example that I want us to look at is a design pattern. And I don't know if you've looked at design patterns yet in this class. Yes? Okay, so you've been looking at design patterns already, so like adapter and singleton and factories and all sorts of design patterns that nobody actually wants to really use in practice, but we're going to take a look at design patterns today, and the specific design pattern that we're going to look at is a resource pool. I'm not actually sure if you talk about this design pattern in software engineering. It's one that is a pretty practical design pattern. So a resource pool is a design pattern that is effectively trying to amortize the cost of creation of objects or resources. Amortize, this word means I'm going to take something that's really, really expensive and I'm just going to reuse it a bunch of times. I'm going to make it once, and then I'm going to reuse it a bunch of times. And then every time I reuse it, the cost per use is reduced overall. So it takes a lot of time to make it in the first place, but if I use it 100,000 times, I can effectively say that I've divided that cost of creation by 100,000 times. So creating some instances of objects can be quite expensive, especially when we need lots and lots and lots of them. This is commonly applied in web applications. So connections, for example, are expensive resources to create. I think you're working on iteration 3 right now. So you're starting to build up a real persistence layer, maybe using SQLite, maybe using HSQLDB. You're using some kind of real persistence layer. And to do that, or if you're not taking 3350 right now, maybe you've taken 3380 before, you have to make a connection to your database. When you're making a connection to your database with like one client, which in this case would be the app that you're building, it's not that big of a deal. But when you're making many, many connections to a database because you're running a high performance web application, Suddenly you've got to make lots of these connections. And the cost of making a new connection to the database is overwhelmingly expensive compared to, I want to send a response to the client as soon as possible. If I open up google.com, there's a bunch of web database transactions that are happening in the background here, kind of saying like this account logged in. They don't want to make a new connection to the database just for me to get to google.com. They just want to have a connection sitting around and waiting for me so that I can start using that connection immediately and start running queries. Another example is files. We have spent some time with files. You have some sense of the kinds of things that need to go into opening a file in a file system. And moving around back and forth between the FAT and the directory entries and the cluster heap is kind of an expensive set of operations to do. So opening a file once and then keeping that thing around and reusing it a bunch of times, every time you call read, you don't want to reopen this file. It's going to save a little bit of time overall. The other one is threads and processes, and that's what we're going to focus on with this design pattern today. Threads and processes aren't super expensive to launch on operating systems these days, but if you need to make lots and lots of threads, you have lots and lots of work that you need to do, constantly creating and waiting for threads or processes, the cost of doing that action itself is going to add up to a significant amount over time. And so the idea of a resource pool is let's just take that thing and try to reuse it over and over and over again. I'm going to make a bunch of instances of these things when I'm starting up this resource pool. And then when the task starts or when I need this connection, I'm just going to reuse one of the things that's already in the pool here. I want us to build a thread pool. So this is an actual thing. If you, I'm not sure what kinds of stuff you've done in Java or other languages in either co-op work terms or in 3350 right now, but you might have seen a class something like an executor service in Java. You may have seen this, maybe, not necessarily. You might have seen this idea of resource pools in Python, again, working with web applications. I want to build a thread pool specifically. I encourage you to follow along. I've pushed some changes to the thread management repository that have what we're going to be working with. And what I want to do to start is to take a look at the interface that we're going to be implementing. And then I want to spend some time thinking about approximately what the structure of this looks like visually, and then we'll start building this thing. So I'm going to pop over to my terminal here. I'm in the thread management repository right now. And today what we're going to be doing is spending some time in this directory that's called 3430 pool. There are a bunch of things in this directory. The very first thing that's here is a type that's called jobqueue.h. Jobqueue.h, it's a queue. It's a queue. I'm not going to dwell on this. It's just a linked list data structure implementation of a queue structure. It has enqueue operations and dequeue operations. We are going to be explicitly using this job type, so I've designed this queue so that it uses this job type that we have. The job type itself has a pointer to a function. This is ultimately what our tasks are going to do when they're running. And there's a void pointer to an argument, and this is what's going to be passed to that function. The signature here you might recognize as being really, really similar to pthread create. This looks really, really similar to what the pthread create signature looks like, and it is the same signature as what pthread create does. And we're going to be using jobs that look a little bit like that. There's also a test for the queue itself. You're welcome to look at this if you want. This is my terrible attempt at testing this queue structure. The other thing that we're going to be building here is and implementing is 3430pool.h. So the first thing that appears here is the thread pool type itself. Unlike the job type, I don't want people using this library to know what my pool looks like internally. So I'm just saying here, there is this type. We're going to have pointers to it. I'm going to give you a pointer to it. You're going to give me pointers to it, but you don't need to worry about what's underneath there at all. we're going to have to be able to create a new thread pool. Creating a new thread pool is going to allow us to specify how many threads we want to start when the pool is created. So if I say here that I want to make a thread pool that has 4 threads in it, as soon as this is starting, I'm going to make 4 new threads. These threads initially aren't going to do anything. There's nothing for them to do yet. They're just going to sit there and kind of wait around until there's actually work to do. But I'm going to create them all initially as soon as I'm creating this thread pool. Once I've created the thread pool, the next thing I'm going to want to do is I want to start sending jobs to the pool. I want to start sending tasks to the pool. The tasks are function pointers with arguments that I'm going to pass to the function. And this is what the threads that are currently idling, doing nothing, this is what they're actually going to start doing. So as work is getting submitted to the pool, I want my tasks, my threads to wake up, and I want them to start actually doing this work. The idea here is that I'm going to have 4 threads, some limited number of threads, and this function is going to queue up tasks. There might be a million tasks that I need to do, but I'm only ever going to have 4 threads operating on them. A thread is going to pick up a job from this queue, it's going to do the work, and then it's going to check to see if there's more work in the queue. Then it's going to pick up a new job, then it's going to do the work, and then it's going to check to see if there's more work in the queue. If there's no work in the queue, it's just going to go to sleep, and it's going to wait until there's more work available to it. So when I submit work to this queue, what I want to do here is I want to signal to the threads that are sleeping right now, hey, there's work for you to do, so please wake up so that you can do this work that I've asked to be done. The last operation that we have here is wait, and this looks a lot like what join does. This effectively says, I want the work that's currently in the pool to just be done. I'm not going to submit any more work, so I want all the threads that are in the pool right now to finish the work that's available for them to finish, and then I want the pool to shut down. I want to destroy all these threads, and I don't want to do any more work after that. So I'm going to open up another terminal to the side here, and I'm going to open up a consumer to this interface. So pooladder.c is something that uses the interface that we're going to be implementing here. I'm going to scroll down to my main function. My main function here creates a pool. I'm going to have 2 threads. So threads is this preprocessor directive at the top. I'm going to make some number of threads. I'm going to submit some number of jobs to the pool to be executed or to be run. And then after I've submitted all that work, I want to wait for all the threads to finish all the work that I'm going to do here. The work that I'm actually asking them to do here is this function. And this function looks a little bit like that textbook sample that we've seen before, but this is just busy work. I really just want to have something that is going to cause tasks to take a little bit of time to finish before the next task gets picked up by the system. So this is just a loop. I've got a lock around adding to the global file scope variable here so that we're not going to have these situations where we have lost adds. Is that okay with everybody so far? Okay. So visually, what this is going to look like is I'm going to make a new thread pool. When I make a new thread pool, the tasks that I have here are to initialize a queue, and that queue to start is empty. These are going to be the tasks that I'm actually asking to be done. The other thing I'm going to do is I'm going to make threads of execution. In this case, I'm going to make T1 and I'm going to make T2. So I'm making 2 threads of execution here. I'm going to create these threads. both of these threads are immediately going to suspend themselves. Because there's no work. There's nothing in the queue for them to do, so they should just wait until there is something in the queue for them to do. The queue structure here is going to be used and manipulated by both the threads that are in the pool and the main thread of execution. The main thread of execution doesn't know about the queue, but I'm going to start calling functions from the main thread of execution that will manipulate the queue. So step 1 is make that new pool. Step 2 is going to be submit new tasks. Submitting new tasks here is effectively adding new nodes to my queue. So I'm going to enqueue new things to my queue. So my queue structure here is going to change, and it's going to have something like task 1 enqueued to it. We're going to want to signal to the threads that work is available. We're going to have to lock this queue while we do that, because our queue is a shared resource among all of the threads that we've got. So I'm going to lock the queue to enqueue something. I'm going to keep the lock to signal with a condition variable to these other threads that work is available. And then I'm going to unlock this lock. I'm done manipulating the queue here. After I submit new tasks, then the thread pool itself, the threads are going to take the tasks. So I'm going to say T1 takes the task. It's going to manipulate the queue. It's going to dequeue something from the queue. And so we're going to want to lock this queue again before we actually do that. But we're going to be using condition variables here. So when the signal is sent, thread 1 is going to receive this signal, and it will hold our lock so it can do stuff to the queue structure. Nobody else is going to be working with the queue structure at this point. Q1 is going to take that task, and then it's going to unlock the lock, and then eventually we're going to wait for all tasks to finish. Waiting for all tasks to finish is effectively here spin on finishing tasks. So the threads of execution, as they finish the task that they're working on, they should just immediately get a new task. They're not going to have to go to sleep because there might be something there. And if there's nothing left in the queue, they will exit. At that point, they're going to finish up. They're not needed anymore, and they're going to exit. Waiting for all tasks to finish in our main threads, this is a blocking operation. So my main thread must wait for all of the tasks to finish before it's allowed to finish up printing everything out. All right, so I'm going to go back to my terminal. And what I want to take a look at is 3430 pool.c. This is the file that we're going to implement this thread pool in. I'm just going to use the queue. I'm not going to step through the queue implementation because it's a queue. We've seen it a bunch of times before. There's no good reason for us to take a look at that right now. So I'm going to spend time just in here, and we're just going to assume that we're able to call enqueue and dequeue and create this queue from the interface that we've got here. I'm going to scroll down, and what I'm going to take a look at first is the thread pool create function. So thread pool create We're not going to do this one. It's already filled in for us, but I've got condition variable and a lock. The lock is going to be for the pool itself. Anytime I want to make changes to the queue structure of tasks that I have, I'm going to have to use this lock. I don't want anybody else manipulating this queue structure while I'm manipulating it. I also don't want anyone manipulating it while I'm reading the queue. If I'm in the middle of trying to find something or dequeue something or count how many nodes there are in this queue, I don't want somebody dequeuing or enqueuing something to this queue. I want to make sure that me reading the queue is an atomic operation. I want to make sure that dequeuing something from the queue is an atomic operation. I want to make sure that enqueuing something to the queue is an atomic operation. I don't want anybody else working at the same time as me in those cases. So I'm going to use this pool mutex to protect the queue itself. My queue doesn't have any concurrency mechanisms built into it. There's no synchronization. There's no locks. I am going to have to be responsible for doing all that locking in this code. I'm going to use this condition variable that's called workCV to signal to the threads that are waiting that there is work for them to do. Wake up, there's actually something in the queue. Please get something from the queue and start working on that task. There's a queue of jobs here. There's a flag that says wait. This is effectively saying somebody has called wait, and so you should finish up what's there, and then eventually we're going to shut down. And then there's a number of threads. I'm using this for simplicity's sake later when we're working on this. I want to keep track of how many threads we're going to be starting up in this pool while we're running right now. Eventually, then, we're going to start creating all the threads of execution here. And all the threads of execution are going to start working in this worker thread function. So that's our third argument to pthread create here. If I'm passing 4 to this, I'm going to make 4 new threads. And what I want all 4 of these new threads to do is I want them effectively immediately to just all go to sleep. So our create operation makes this empty queue for us. It creates all these threads. It starts up all these threads. And now our task is going to be to implement what our thread itself is actually doing here. All right. So I've got an assertion here. I don't want someone to send to me a null pool. I want to make sure that the pool that's given to me is actually a thread pool that I can work with. Once I've got that assertion set, I'm going to start working on this as though it is a loop. The loop that I want to run here is while pool is not equal to null, and we're not in a state where we're shutting down. So the pool right now has this field pool wait. Pool wait. Pool wait is this flag that we're going to set when we're shutting down. I want these threads of execution to just keep checking to see if there's more tasks as long as we're not in the process of shutting down. While this is happening, the first thing my worker should do is check to see if there are any tasks in the queue. If there are tasks, then do the task. If there are no tasks, so our queue is empty, go to sleep. Wait until there is actually something for you to do. I want to check to see if there are any tasks in the queue. And to do that, I'm going to have to lock the queue. Again, I do not want anybody changing the queue while I'm trying to read it. So I'm going to say pthread mutex lock. And what I'm going to pass to this is pool mutex. So pool mutex, this is the name of the lock structure that we're going to use to lock everything about this pool that we've got. I don't want anybody else to change the number of nodes while I'm actually counting the number of nodes that are in the queue. So I'm going to acquire this lock. And then what I'm going to say here is while the number of nodes, queue size is the way that we're going to ask how many nodes are in this queue. While it's equal to 0, while there are no tasks for me to do, and I'm not shutting down, if we enter this loop, we're in a state that the queue size was 0. There are no tasks. There are no jobs. I'm just one thread. I've counted. There's no jobs in this queue for me to do. And so I effectively want to suspend myself. I want to go to sleep. I want to allow jobs to be submitted here. So I'm going to say pthread cond wait. I want to wait on a condition. The condition is going to be pool work CV. This is the one that we initialized in our main function or in the creation function. And I want to pass this lock. Okay. So we get into our worker function. Pthread create is called. We're starting this thing up. I've entered the worker function. The first thing I'm going to do is that assuming we're not currently shutting down, I'm going to try to acquire the lock. If I can acquire the lock, I'm going to ask how many nodes are in this queue right now? How many jobs have been submitted? As it's starting up, this will be 0. There are no tasks in the system right now. The main thread hasn't tried to submit anything yet. If there are no tasks in this system right now, and we're not in the state of shutting down, then I want to go to sleep. I want to be notified when there are tasks in the system, but I don't really want to do anything right now because there is nothing for me to do. The semantics of pthread cond wait here are, I would like to wait for this work CV to be signaled. This is the lock that I'm going to use for that. I would like you to suspend me, and I'm going to give up control of this lock. I don't hold the lock anymore, so I'm suspended. I'm going to move down. So at this point, our threads are going to get blocked. They're stuck. They're waiting around for work to be submitted. I'm going to move down. To thread pool queue here. Thread pool queue is the function, thread pool queue is the function where I'm going to be submitting a new task to be executed. This is where I'm going to manipulate this queue, insert a new job, and then I want to tell our workers that there's a new job. There's a new job. You should wake up and take this new job and actually do it. So to do this, I'm going to start by checking to see that these things are not null. I want to make sure that the pool that's being submitted to me is not null, and also the function that's being submitted to me is not null. If neither of these are null, then what I'm going to say is that the job that I'm working with here is something I'm going to dynamically allocate. So I'll use calloc for this. I want to insert one new job into my queue, so I'm going to allocate this new job. If I was able to allocate this thing, then what I'm going to say is that the job func, this is the name of the function, or this is the function pointer that I want to be executed, is equal to the function that was passed to us. And I want to say job arg is equal to the argument that was passed here. So when I'm queuing this work, I don't want it to happen right away. I just want to take a copy of it so that I can give it to one of these worker threads that we started up in our creation function. So I'm just going to take a copy of this, and then ultimately what I want to do here is enqueue this thing. We want to enqueue the new job that we just accepted. We're going to manipulate the queue. So we need to acquire the lock. So I'm going to say pthread mutex lock. I want to acquire the lock that is the pool itself. I want to enqueue the task. Jobs is the name of the queue that I want to enqueue this to, and job is the thing that I want to put into this queue. I've added the job to the queue, signal to workers that there is work to do. So I'm going to say pthread cond. We've got two options here. We've got number one, signal, and number two, broadcast. I'm going to ask you, because everybody's looking real mighty sleepy right now, which one should we do? I've got, you just like jumped your hand up immediately. I'm going to ask everybody. I've got 4 threads that are sleeping right now. There are 4 threads sleeping. I've just added one task. Hold up one finger if you think we should do signal, and hold up 2 fingers if you think we should do broadcast. On the beat of 3, please, everybody. So 1, 2, 3. Okay, it actually doesn't matter. So I see lots and lots of ones, and actually that does make more sense than waking everybody up. Let's just wake one of them up. Let's wake one of them up that's sleeping rather than waking all of them up that are sleeping. We could do either. If we wake up all of them, one of them is going to get the lock. It's going to get the job. The other 3 in this case are all just going to say, there's nothing there, so I'm just going to go back to sleep again. So I'm going to say signal. I want to signal to the work condition variable, so pool arrow pool work CV. Wake somebody up. Hey, there's a task. Somebody please wake up and take this task. Once I've signaled that, I need to release the lock. Once I've done that, I'm going to say this function returns something. So I'll say status is equal to 0, so that when I get to the bottom here, I'm going to be able to return status. Okay. In this system, in this contrived system, I'm saying there are 4 workers that we created when we started this. I'm going to ask you, just by a show of fingers here, there's 5 fingers on your hand. how many threads of execution are running in total in this system right now? How many threads of execution are existing in this system? Maybe that's a better question to ask. Okay, so 5. There are 5 total threads of execution running in the system that are in the system right now. Which of those threads of execution is running this code? Just like M for main, like this. Yeah, M for main. Everybody M for main. Okay, M for main. The main thread of execution is the one that's doing this. So our main thread of execution is submitting a task. Our main thread of execution is running this code. This isn't some special thread that gets created when we're calling stuff in our thread pool. It's actually my code. It's my time on the processor. It is me that is running this code. I don't know what this code looks like, but it's my thread of execution that's running this code. So my main thread of execution acquires this lock. It manipulates the queue. It sends the signal. It unlocks the lock. And then eventually, control kind of returns to us in the form of this function gets returned from, and then I'm starting to run my own code again here. So now we're in the state of, I've started these threads of execution. Threads of execution have gone to sleep. I've submitted new jobs for these threads of execution to take, and I've signaled to them that they should wake up. So after this, after this, after line 115 and after line 116, some thread of execution is going to wake up here. On line 50, a thread of execution will wake up that is currently waiting for this condition variable. And it's going to go back to the top of this loop. When this thread of execution wakes up here, it has the lock. It holds the lock. And so I can start interrogating, I can start asking questions like, how many nodes are in my queue? How many nodes are currently in my queue? And I don't have to worry about somebody making changes to it underneath. Yeah.
So on line 115, you wake them up, and then on line 116, you unlock the pool. What happens if the scheduler starts the next thread to unlock the pool?
You didn't miss anything. So the question is effectively about order of operations here. What happens if we send the signal here on line 115, but before we can unlock the lock on line 116, some thread of execution actually gets scheduled and wakes up? The semantics of our condition variable is that it will not proceed past that point because it does not hold the lock. And so even if it is actually scheduled by our operating system, is not going to do anything. It won't proceed past that point. It's going to sit there and do something like spin lock. It will just sit there and wait until it's able to get the lock. It will then eventually get taken off. It will be preempted, and our main thread will get control again, and it will proceed to unlock the lock. But until this lock is available, we're not actually going to return from pthread conwait here. So the semantic of this is that we will always hold the lock when we have returned from pthread mutex, from pthread conwait, sorry. Okay, so this thread of execution wakes up. It's going to ask, are there tasks in the queue for me to do? Yes, there are now tasks to do. Queue size is not equal to 0, so we're going to exit this loop. I'm going to exit this loop. And I'm going to ask the question again. Are there jobs for me to do? There are 2 conditions that I could be leaving this loop for. One was we're shutting down, so please don't do anything else, or please finish up what's there. The other condition is that there's no jobs left in the queue. So I still want to ask the question, is queue size for pool jobs greater than 0? If there is a task for me to do. This is some thread that we have in the system that we created. There is a task in the system for me to do. And so what I want to do here in this threaded code is I want to say job is equal to DQ from pool jobs. I want to take this job. Yep. That's a great question. Should we put a lock around this? I'm going to step through these lines. I've locked the lock. I'm still going to step through these lines because I want to make sure. I've locked the lock here. I'm going to ask questions. I hold the lock. There's no work for me to do. I'm going to go to sleep and release the lock. Somebody signals me, hey, there's work to do. I hold the lock. I'm going to ask, are there jobs for me to do? Yes, there are jobs for me to do. Exit the loop. I still hold the lock here. I still hold the lock. So I can ask that question and I can manipulate the queue. I can dequeue this task without worrying about anybody else making concurrent modifications to it. I'm going to dequeue that thing. And then what I've got in my thread itself, is I've got a job, an instance of a job. I've got a function, and I've got an argument that I want to use for this. So I'm going to say that I want to dequeue some job from this set of jobs. Once I've got this job, I'm going to say that the function that I want to invoke is equal to job_func. I'm going to say arg is equal to the job arg itself. And once I'm done working with this, I'm going to release the lock. I have the job. I've finished manipulating the queue. I want to let somebody else be able to use or manipulate the queue structure that I've got here. So at this point, I'm going to say pthread mutex unlock pool mutex. Whoops. So our state here is that we've just signaled this new task to be started. We unlocked that lock in the main thread of execution. That thread of execution woke up from pthread cond wait. There was a job for it to do. We dequeued the job. We took the job. We unlocked the queue so somebody else can make changes to it. Now I want to do the job. I'm going to call the function pointer. The function pointer is the task that I want to complete, so I'm going to call the function pointer. My thread of execution here is now going to start executing this function. So on the right side of my screen here is that pool adder.c. When I call job and I pass arg to it, I'm coming back to here and I'm going to start doing this work. When I queue with thread pool queue, the function pointer I'm passing as work, which is this one, we're jumping back over here when I actually call that function pointer and we're starting to run this function. How are we doing? Is this okay still? Concurrency breaks my head. It really does me in. And so I want to make sure that we're all approximately on the same page here. So we've got these 5 threads of execution. We've got main. Main is the one that's going to eventually be calling thread pool create, thread pool queue, and thread pool wait. And then this function that we've got here on this side, this is only ever going to be executed by these additional threads of execution that I've created. We're all working with this common central thread, this jobs queue, sorry. And we're all collectively manipulating this jobs queue. So at different times, we're going to lock it, we're going to make changes to it, and we're going to dequeue stuff and enqueue stuff from it. All right. So if I was able to get the job, I got a job, do the job, call the function that was passed to me, take the job off the queue, take the argument off the queue, call the function, do the job. Once you return from the job itself, so the task that you were given eventually finishes, what we're going to do here is zoom back up to the top of this function. We're going to ask this question, are we shutting down right now? We are not. We're going to try to acquire the lock. If we get the lock, we will ask the question, are there jobs for me to do? If there are no jobs for me to do, I will go back to sleep. If there is jobs for me to do, so there was a bunch of jobs that got submitted. If there's something for me to do, don't bother going to sleep. Don't even enter this loop. I hold the lock, ask how many jobs there are, get the job, do the job. And then just cycle. Yeah. That's a great question. Can we do this? Sure, we could, yes. But the effect of this now is that this long-running task is going to run while we hold the lock. And nobody else is going to get to take any more tasks off of this queue because we have some long-running task that we're doing here and holding the lock at the same time. This effectively means that only one thread is ever going to get to run its task at the same time as the other threads of execution. We don't really want that to happen. I want to put it down here because I want the threads kind of like only to manipulate the queue with the lock. And once they've manipulated the queue, they've taken the job from the queue itself, release the lock, and then do the long running work that you're going to do so that other threads can get a job and do their work at the same time as us right now.
As long as it's not a shared resource in that function.
As long as there's not a shared resource in that function. So when we were looking at this code here, we have a shared resource here in the main code block itself, but this is only going to be like 3 instructions that we're locking here, as opposed to the loop, which is what really takes the big amount of time. Yeah. Yeah.
So why are we assigning the job func to func and job arg to arg? That's not manipulating the queue at all, right? So
that could go here.
Okay.
Yeah.
So just making sure that it
that could go here. In fact, I don't really necessarily even need to have these things. I could do this. And this would accomplish the same thing. But this looks a little bit more foreign than just calling a function than the way that we normally would. So I'll leave it like this to make it clear that really the only thing that needs to be locked is the dequeue operation. Yeah. Yeah. If I send a signal to the threads, but nobody is sleeping right now, and so that would be a normal condition for this to take place. If I submit, if I submit new work and I send this signal here, if nobody is currently waiting on the condition variable, then the side effect is effectively nothing. Nobody's waiting on it right now, so there's no one to receive the signal. Everybody is currently awake. If nobody receives the signal, then they're just going to get back up to the top of this loop and just to check again to see if there's work, because they're already awake and running. They're already doing something.
But if let's say like there's one thread in circle and it gets to well inside a job with zero and there's no work. It goes like after that line, it stops and goes to the next context and then it pushes work on it. Like right after it checks if there's no work.
So if just after I've checked that there's no work here, yeah. So if this is false, if it's equal to 0, then I'm going to exit this conditional statement. We might get interrupted at some point here. Somebody else will add. So this function here might get called. Our thread pool queue operation might get called. If thread pool queue gets called, we've manipulated the queue and we've added something to the queue. And our one thread of execution takes over again. It's going to come back up to the top of this loop. It's going to get the lock. This is going to be false, and it's going to ask this question again.
Oh, no, I mean like after line four, and before next line 50, can you send a signal?
So before we, so between 46 and 50, can we send the signal? So that's possible, I guess, yeah. But no, it's not possible. It isn't possible because that thread of execution holds the lock. This thread of execution holds the lock, and before we're even allowed to send the signal, we also have to get the lock. So my main thread here is going to be stuck waiting for the lock to be acquired. If this one is currently asking, are there any tasks in the queue? If there are no tasks in the queue, it will get suspended and it will release the lock, allowing this thread of execution to then enqueue something and then signal to it because it's sleeping to wake up because there's something in the queue. Yeah. You almost had me there. Yes. Concurrency breaks my head. Yes. Yeah. Yeah. One. Yeah.
So if you reach the peak thread condition wait, but you send a signal to it, let's say there's one thread operation already operating, you send a signal to that to wake up, but it's already awoken. But this thread now wants to go to sleep. Is there a queue inside of there that says, oh, don't go to sleep? Someone sent a signal previously to wake up.
So we're never really going to be in that state because of the lock around getting it in the first place. So let's hypothetically say I'm right now doing this hard work. I'm spinning around counting up with the worker that I've got here. I'm stuck on line 19 spinning on this loop for billions of times so that I can get some hard work done. If I'm spinning on this work, I don't currently hold the lock, but this thread of execution is going to have to get the lock. If it gets interrupted at this point, so it's trying to enqueue something and it is interrupted, and I'm given control back and I return from this function, I'm still going to go back up to the top of this loop and I'm going to try to acquire this lock, but I can't acquire this lock because somebody else holds it right now. So I'm going to get blocked here. Once this thread gets control again, finishes enqueuing, signals to me, and then sends the lock, unlocks the lock, I will be allowed to proceed past this point, but the queue size is already increased. And so I never need to go to sleep again because there's just work for me to do. I will never enter this loop in the first place to go to sleep. So I don't have to ask, has somebody signaled me while I was doing something else? Because if somebody would have signaled me while I was doing something else, they would have done it because they made changes to the queue structure itself. Do I understand your question correctly? Okay. So if I did that, I guess effectively how many threads would get woken up or woken up? It's not going to keep anything awake for longer based on the way that we're using the lock structure around signals in the first place. Yeah. Okay, all right, okay. Okay, so we are now in a state where we've been able to get work, we do the work, and now what we want to do is we want to get to a point where our main function wants to block. It wants to wait for all of the work to be done that has been queued previously. So I'm going to show this pool adder again. And the way that this works is that I'm going to submit to this thread pool total jobs. Total jobs here is 10. There are 10 jobs, but each job is going to count to 200 million. Every job is going to count up to 200 million, and there's only 2 threads of execution that I want to be executing at any given time in this thread pool itself. So I'm going to start up these tasks. As soon as they are submitted, they're going to start waking these threads up that were previously sleeping. But after I've done that, because all I'm doing here is manipulating a queue, my main thread of execution is going to finish this loop pretty quickly. On this line right here, I want to wait for all these threads and all of these jobs to finish. I want all the work in this system to be done. Yeah. It's possible. So the question is it possible for my main thread of execution to queue up all of these tasks before any thread is even allowed to wake up and start taking tasks? Sure, absolutely it is. And that's why we want to wait here.
If you queue all of your jobs before any of your jobs are waitable.
Yeah. Concurrency is breaking my head, and I can see that it works the same way in your brain as it is in mine right now. If my main thread of execution is indeed able to make changes to the queue, oh no. Okay. I'm trying to use tmux splits and vim splits at the same time, and this is also breaking my head. If I was able to submit all this task, all of these tasks in the main thread of execution before any of these threads actually got to start. So let's say we started up 5 threads and they all just got stuck on this assertion. They weren't actually even able to enter the loop to start asking questions about it. If I was able to do that, and then eventually they started to get access to it, they'd all queue up here. They'd all get stuck on this lock. They'd all be asking the same question, is there work? Yeah, exactly. Okay, so the state that we were in here a moment ago was, there is no more work. I'm not going to submit any more tasks, but whatever tasks there are in this system, I want you to finish. I want you to finish this because I submitted this work, but I don't want to proceed past this point until all of this work is done. And so thread pool wait here is an operation that I want to be blocking. I want my main thread of execution to get stuck here until all of the tasks and all of the work is done. So what we're going to have to do here is implement our thread pool wait function. And so I'm going to go back to my vim split here, and I'm going to start implementing this function. So if the pool is not equal to null, then I'm going to say pool wait, so this is that flag, is equal to true. I want you to shut down. Anytime you get back to the top of this loop, I want you to start shutting down because we're done. I don't want to submit any more new work to this thing. It's conceivable that all the threads were done already, and they're all just stuck waiting to see if there's more work to be submitted. They're all stuck waiting on this condition variable. And so what I'm going to do is this. While pool, the number of threads that are currently running in the pool is greater than 0. So this was something that we set when we created the pool in the first place. While the number of threads is greater than 0, I want to get the lock. I want to send a signal to wake them up. And then I want to release the lock. Effectively, what I'm doing here is wake everyone up so that they see that the flag has been set. I want everybody to wake up so that they're going to eventually check to see, are we shutting down right now? This is now assuming that once these threads are finished, they're going to make a change to this value that says that they are done. And so just after exiting this loop, here's our condition here. We were currently sleeping because there wasn't work when we went to sleep, and we weren't shutting down when we went to sleep. But somebody woke me up. Somebody woke me up, and now I see that the pool is shutting down. Pool wait is true. There are no tasks to do, but the pool is shutting down. I'm going to ask this question, are there tasks to do? There are no tasks to do. I'm going to go back up to the top of my loop here, and I'm going to ask that question, are we shutting down right now? We are shutting down right now. So I'm going to exit this loop. And now I have to tell that main thread that I am indeed exiting. My thread is going to return. It's returning from the only function that's on its stack right now. I'm done. So what we'll say here is pthread mutex lock. I want to say pool threads, pool end threads, minus minus. And then I want to unlock the lock. I could avoid using these locks if I'd set this as an atomic value as opposed to using just a uint for this. All right. We have a semi-complete thread pool here. It's not going to work. It won't work. I'm going to quit this side. And I'm going to open a new terminal here. I'm going to change into 3430 pool. I'm going to make this. I'm actually quite relieved that it compiled it all. It's still not going to work. I'm going to run pool adder. And my expectation with pool adder, and I'll make this again because I did make some changes to this. My expectation with pool adder is that I'm going to be about to submit a bunch of jobs. I'm going to queue all these jobs, and then I'm going to wait for those jobs to finish. And then my total sum should be 10 times 200 million. So it should be 2 billion. 2 billion. It should be 2 billion as the sum at the end. And there's going to be 2 threads of execution that are working here. And it's actually kind of working, but you might notice here that we're getting into states where these values are different, which isn't really what we want. I'm going to come back to this code tomorrow. And there are a few other places where we're going to need to add some additional checks here. And I'll leave this as an exercise for the reader right now, if you're interested in trying this out. There are some places in this code, so this is worker thread. And I'll write this down, exercise for the reader. It's possible for us to acquire a lock and not release it. It's possible for this to happen. And the other thing I'm going to add here is, in the wait function, 2 things. This is ultra inefficient. this is just going to spin. If there's a bunch of work that's left for me to do, this is going to spin and spin and spin and spin. Acquire the lock, send the signal, unlock. Acquire the lock, send the signal, unlock. Acquire the lock, send the signal, unlock. And it's just going to keep spinning until all these things are done. If I'm in a state where, for example, I change the amount of work or I change the total number of jobs here to be significantly higher, well, you can actually see we're orders of magnitude off here. We're not actually finishing all the work that we're supposed to be doing. But we could be in a state where we're just constantly spinning on this. So this is ultra, ultra inefficient. And it's also causing our threads to exit before all the work is done. It's causing our threads to exit before all the work is actually finished. So I'm going to come back to this tomorrow, but I'll let you dwell on this if you want to dwell on this overnight. The other thing that I wanted to do today is I wanted to take a look at assignment 3. Oh, let's all take a deep breath. Let's just all take a deep breath. I really do like taking the time to do like big worked examples, but they are draining, I think, for everybody involved. I think they're draining for everybody involved sometimes. I like it because they are illustrative, they are informative, they give an idea of the bigger picture, but oh my God, they're boring to sit through. And yeah, it's actually quite stressful for me to make sure that I'm not like missing stuff. So we'll just keep doing it tomorrow. We'll just keep doing it tomorrow. In assignment 3, what I want you to do is I want you to start building up concurrency yourself. The concurrency that you're going to be building up here, to be very clear, is not at the same time concurrency, it's at the same time concurrency. You are going to be building an implementation of a threading library, and the threading library that you're implementing will work within a single thread. So what we're effectively building here is a single CPU implementation of concurrency. So this is effectively just operating on one single CPU. The idea is that I'm going to give you an API that you have to implement. So this is similar to some of the other stuff that I've asked you to do. But the API that I'm asking you to implement in this case effectively looks like the pthreads API. I want you to be able to make a thread of execution. I want you to be able to ask for that thread of execution to do some work. I want you to implement locks so that when these threads of execution are actually working, that they are going to be able to prevent concurrent access. The threads that we're implementing are not preemptive threads. They are not preemptive threads at all. We are going to be implementing cooperative multitasking. Cooperative multitasking is multitasking where the tasks or the threads themselves are giving up control of the CPU. The CPU is never being taken away from a thread of execution, but instead the thread of execution will voluntarily yield the CPU. The implementation that the interface that I'm looking for you to implement is up here in assignment 3 template. There are a few different files that I'm looking for you to implement. The first is nqpthread.h. And there are 2 functions in here. One of them is to create a thread of execution, and the other one is to join a thread of execution. So create takes a function pointer as an argument, and it takes an argument. This should cause a new thread of execution to be created in your system and then be eligible to be scheduled by your system. The NQP thread join is a blocking operation just like pthread join is, and it should wait for that thread of execution to be finished the work that it's doing. NQP thread schedule has a bunch of different stuff in it that we're going to be working with in terms of scheduling. I'm going to be asking you to implement a few different scheduling policies. We'll talk a little bit more about these scheduling policies in the next couple of days, but the idea here is that after I've created a bunch of tasks, I'm going to initialize my scheduler with the policy that I wanted to use. I'm going to cause all of my threads to be started to be executed. Eventually, these threads are going to call yield. And yield is, I'm done now. I'm going to give up control, and I want someone else to be allowed to take over on the CPU. Once the threads are done, they're going to call exit, and exit is effectively saying, I am no longer eligible to be scheduled. I'm going to be finished now, so you shouldn't try to schedule me anymore. In this repository, there's also a locks header, and the lock implementation here looks a lot like pthread mutex lock. With these lock implementations, the things that I want you to do with this are to implement basic spin locks. And I'm going to go straight up and say that if you look in the chapter in the textbook on spin locks, you will find the actual implementation. Your job here is basically to copy the textbook. It's to copy parts of the textbook. So that's good. That's really good. The locking stuff is actually straightforward to do. The key here is that I want you to implement this using atomic values. I want you to use a header that's called stdatomic.h. And I want you to implement this so that it works with either pthreads or with NQP threads. So in either case, so using it as a lock for real or using it as a lock in the context of our threading library. There are a bunch of different tests that I am going to give to you that will use the library that you're implementing. I'm going to pull up NQP printer here. This is the very first one that I'd expect you to have working. This is not an exciting library to, not an exciting test to actually run, because all this does is take two threads of execution and switch back and forth between them. Each of these tasks prints out the letter A or the letter B, and it prints out a counter. And the purpose of this test is to see that we can actually switch back and forth between A and B, but also that there's state maintained between each of the switches that we do here. The whole thing is I want you to implement this using some functions that are provided by our operating system. There's a function here that's called getContext. This is available on Linux. This is a Linux-specific thing, so you'll have to continue using your Linux installs. GetContext is thankfully the way that we're going to get the state of our processor. We're not going to actually have to do like capture the state of the processor so that we can put this into our thread control block. We're just going to rely on some functions to do this for us. The other function that we're going to use in this assignment is swap context. Swap context and make context is the other function. Swap context and make context are effectively, make context says, given this context, I want you to start running in this function, and I want you to pass some arguments to it. Swap context is, I want you to take the context that's on the CPU right now and switch it with this one so that it retains the state that you're working with. In terms of getting started with this assignment, I would say that it's possible for you to get started working on the locks part of this right now. The locks part of this right now is to do spin locks. It's basically to implement spin locks and to use pthreads to build up a test program to work with this. And then once you get past that point, then you could start working on the thread stuff itself. I'll spend a little bit more time talking about this in the next couple of days, but ultimately, I'm looking for you to implement a few different scheduling policies to be able to work with that. I want to show you really quickly what the output I would expect from this to be. So this is NQP printer, and the idea with this is that it's going to print out for thread A up until about 50, and then it'll switch to thread B, and then it switches to thread A, and then it switches to thread B. And when I was implementing this, I was never more excited to see A and B showing up on my screen like this. But eventually what you're going to get to is to start working with some of the other stuff here. So NQP Refiner is the one that I am the most proud of. And NQP Refiner is this. And each of these lines here is a single task in the system. This is a single thread that's running, and each of them are effectively making progress independently. They're all kind of getting switched back and forth to, but all of this is running within one single thread of execution. So there's never actually multiple threads of execution in my code. These are all just contexts that I'm rapidly switching back and forth between. All right. So in tomorrow's class, I will we'll take a little bit more of a look at this thread pool that we started out with, but you should still continue to be able to use condition variables in a program at this point. And then on Wednesday and Monday and Wednesday next week for sure, I'll have time for questions about the assignment, as I've had in the past couple assignments. But I will dwell a little bit more on the assignment a little bit later in class after we've done the scheduling policy stuff. But I wanted to give you an idea of how you could start getting it, how you could get started with this if you wanted to get started with it right now. That's it for today. I hope that you all have a great rest of your day.